Hey everyone, and welcome to Quesadilla Math with me, Mr. Padilla. Today we're going to be talking about function notation and how to evaluate functions in all sorts of different representations. We're going to be looking at how we can extract information from function notation, as well as some of the benefits of using it over just plain old y equals. Alright, well, let's get started. So function notation is another way that we can write equations. One of the first ways that you learn to write equations is just simply using y equals at the beginning of your equation. For example, in linears, we have y equals mx plus b, something you guys know probably, hopefully, very well. In function notation, we are using, instead of y, we are using this symbol. We call this f of x. And it is really just a replacement for y that lets us see a little bit more information from our equations and has a few other useful attributes as well. So let me show you guys what I mean by that. One useful thing about using function notation is that you can differentiate your equations. In Algebra 2, there's going to be a lot of problems or situations where we have to deal with several equations at the same time. And you might find it useful to be able to name them according to what they represent. If we are looking at a cost function, you might want to call it c of x. If we are thinking about a time function, you might want to call it t of x. If we are looking at a height function, you could call it h of x. It kind of gives you a little bit of a hint as far as what the equation is actually talking about, what situation it represents. And it can help you from getting confused when you're looking at a bunch of different equations at once and help you reference it a little bit faster. When we are looking at coordinates, we have to remember that the y values, we really think of them as f of x values now. We're going to be using this f of x notation for everything, and just know that really it's the same thing as y. So the usefulness of it comes in a variety of ways. Just like in coordinates, when you look at something, an equation like f of 2 is equal to 8, immediately you could tell what is the independent, what's the x value, and what's the dependent, the y value. In this case, f of 2 is equal to 8 shows you that 2 is our x value and 8 is our f of x or y value. And we can look at that either way. Really, an equation like this shows us a coordinate point from an ordered pair from our function. We can also use it, if we know the equation, to help us more quickly substitute and solve for certain values. G of x is equal to x plus 2. And if I want to know what g of 2 is, I can just quickly replace my equation 2 with this 2. It's kind of nice to be able to see, oh, okay, I have to plug in a 2 where my x used to be. So anywhere I see an x in my equation, now there's going to be a 2. That can also help you figure out, oh, well, g of 2 is equal to 4. Now I have a coordinate that I can plot on a graph, that I can chart on a table, a lot of different uses. When we have to deal with word problems, a lot of times our equations can give us a hint about what is the relationship of the variables in the situation. If I look at a function name, like r of t, I know that t, what's inside the parentheses here, is called the independent variable. It's your x. Even if the variable itself isn't x, you know that it's we're going to use the x-axis when you graph it. You know that those values are going to be the x values, the domain values. The rest of it, r of t, this is your dependent variable. R would be the variable that would represent your y values in this case. And so you could tell that this is the range. You can differentiate your variables a little bit more clearly and easily see the relationship between them. Which one depends on the other. Here we would say that r is a function of t. Or in this equation, we have g is a function of x. So that means g depends on x, x is independent, g is dependent. Here we can look at it the same way. F of x. So we know x is independent and f is the dependent. So those are just some of the ways that function notation is useful. Let's look at a few ways that we can use function notation to answer some questions about functions. Our first example is going to show us how we use function notation to evaluate a function using a graph. Let's start by identifying our independent variable and our dependent variable. Our function here is called f of x, which means x is our independent variable and f of x is our dependent variable. It's not just f, it's actually f of x. Remember, f of x is equal to y. Same thing. So now let's evaluate our function for a few different values. The way we say this is f of -3. When we look at this, remember, what's inside the parentheses, or the argument of the function, is the x value. So here is our x value. And in this case, our x value that we're looking at is -3. So we can go to -3 on the x-axis of our graph and see where our graph actually exists at this x value. Seems to be this point right here. Really, when we're asking to evaluate via a graph, we're just asking for locations of a coordinate. The x value is -3, gives us a coordinate with the y value at +2. In this case, f of -3 is equal to 2. So now let's try again. This time, we'll evaluate f of 2. We look at our x-axis because our x value that we're evaluating at is +2. And it seems that we have a point on our graph here. This is the coordinate to 5. Since this is my x value, this must be the f of x value, meaning that f of 2 is equal to 5. The third example here, this time we're given f of blank is equal to 0. And we're supposed to figure out, well, what goes into the blank. Since f of blank equals 0, this is our y value. So this is kind of a backwards problem. Instead of looking at the x-axis, this time we're going to approach the y-axis. So we're looking horizontally this time. So our y equals 0. We do have one coordinate point here, -1, 0. So that means the x value that actually gives us a y value of 0 for this function is x equals -1. So now let's evaluate at a point that is actually not on our graph. We're going to try f of 0. So once again, our x value that we're going to be looking at is 0. But if we look up and down along x equals 0, you'll notice that there is no graph, no coordinate at all for our function. F of 0 is what we call undefined. And we can usually abbreviate this with UND. That's how I'm going to be writing undefined in these videos, just to shorten it. So what it means to be undefined is that this particular x value is not a part of our domain. And since it isn't a part of our domain, there is no associated range value for this function. Here I have written in the list form the domain and range of this function. When I have a scatter plot, the best way to describe the domain and range is just to list the values from least to greatest. There are only coordinates for the graph for the function at -3, -1, 1, 2, 3, and 4. So those are the only x values I listed. For the range values, the only y values that are being used by the graph are 0, 1, 2, 3, and 5. So those are the only ones that are listed in the range. Let's move on to our next graphical example. So now we're looking at a graph of w of x, which is part of a linear function that has had its domain restricted. So let's identify our independent and dependent variables again. Again, our independent variable is x, and our dependent variable this time is w of x. So now let's evaluate a few values on our function. So we'll start with w of 0. My x value that we're using this time is 0. And the coordinate on the graph where x is equal to 0 is 0, 1. You might recognize that as the y-intercept. But what this means is that w of 0 is equal to 1. The y value, the function's value at 0 is 1. That's another way we can say it. So now let's find the function's value at -2. So we're going to go to -2 on the x-axis, look for the part of our graph that intersects with that, and it leads us to this coordinate point, -2, -1. W of -2 is equal to -1. So now let's look for the x value that produces the y value, the function value, w of blank is equal to -2. Instead of looking at the x-axis, we're looking at the y-axis at -2. Since it's w of blank, we don't know what. It's w of x is equal to -2. We're trying to find what x is equal to. Going horizontally this time, I notice that I intersect with the graph of the function at the coordinate point -3, -2. The x value, x equals to -3, is what produces w of x equal -2. So now let's try to evaluate this function, w of x, at x equals 2. I'm going to look at 2 on the x-axis, and I will notice that I have what we call an open point, an excluded point. So if you recall from our video on domain and range, excluded points are not a part of the domain, and therefore we consider this to be undefined. So since it's not a part of our domain, it is not defined as part of our function. If we could do the same with other values such as w of 3. W of 3 would also be undefined because there is no graph at all at x equals 3. X equals 3 is also not part of our domain. Looking more closely at the domain, we can see that the only x values we can use are from -4, including -4, only up to 2, but not including 2. That's why w of 2 was undefined. In interval notation, we see a bracket with -4, comma, 2, with parentheses. Our range went from -3, including -3, but strictly less than 3. In our third graphical example, we're looking at the graph of the function p of n. This time, our independent variable isn't x, it's n. And our dependent variable, therefore, would be p of n. So you're not always going to be looking at f and x, or f of x and x, or just simply y and x. Sometimes we're going to need to use different letters to represent our variables for different situations. That way we can give meaning to our equation. Now let's evaluate the function p of x at x equals 6. So I will look at for 6 on the x-axis, look to see if I have a part of the graph on that x value, and it looks like we do here at 6 and 3. P of 6 is equal to 3. Next we can evaluate p of x at x equals 2. Here at 2, it looks like we have the coordinate 2, 0. P of 2 would equal to 0. So if we're being asked p of what is equal to 0, well, we've kind of already answered that question right here. We know that p of 2 equals 0, so that n, be careful, this wasn't x, n is equal to 2. And once again, we are going to look at undefined values, this case p of 5. If you notice at 5, even though there is graph on the left side and on the right side of our x value, at the actual x value we have an open excluded point. So the value at 5 is undefined. We can also see that in our domain, 5 is not included. Our domain goes from -1 to 5, neither endpoint included, and then from 5 to 8, with 5 not being included and 8 being included. Our range, however, goes from 0 and all the way up, without any breaks, to 6. 6 is not included, however, in our range. So the next few examples are going to be of how to use function notation when looking at a function in kind of a table form. We're going to look at a table, a set of points, and a mapping. Very, very similar each and every one. In this case, we're looking at our independent and dependent variable of x for independent and f of x for our dependent variable. And it's once again very simple to evaluate a function based on a table. When we look for f of -5 in our table, when x is equal to 5, f of x is equal to 2. Very, very straightforward. If I want to know f of what is equal to 21, all I have to do is look for the y value 21 this time, and notice that it's paired with the x value 0. F of 3, since our function is being represented only by a table, and the x value of 3 does not appear in the domain of our function, we can't say for sure that there is a function value at 3. Even if you notice there may be a pattern to your table, unless there is an equation that you can use alongside it, if it's not on the table, we must say it's undefined. So once again, you might notice that our domain and range are in list form here, and of course they are in order from least to greatest. So now we're looking at g of v, which is a function that's being represented by this set of points. This time our independent variable is v, and our dependent variable is g of v. If we try to evaluate our function g by using g of 3, we have to look for the coordinate where the x value is 3, and notice that it's paired with the y value, the g of v value, -5. So g of 3 is -5. Same thing applies with g of blank equals -2. We were trying to find out what v value gives us the g of v value of 2. This time I'm looking for the y value of 2, and I notice that it's paired with 1. So v equals 1 is the v value that gives us this function value. And once again, if it's not listed in the function, it is undefined. So here, if I look for g of 0, I will be looking for a domain or an x value of 0. And the only ones that I have listed are 1, 3, and 6, as you can see in our domain here. So g of 0 is undefined. So in this example, we're looking at h of t, which is being represented by this mapping. The independent variable this time is t, and our dependent variable is h of t. Trying to evaluate the function h at -2, we notice that in a mapping, function values are paired with an arrow. So -2, it has an arrow pointing to 5. H of -2 is equal to 5. That's the function's value at -2. We can do the same with using the function value. So here we're looking at h of t is equal to 1. But in this case, I wanted to point out that there's actually more than one solution here. There are two t values that give our h of t values of 1. So in this case, we would actually have to write t is equal to both -9 and 8. Again, let's look for something that's not in our function h of 1,000. Here we would look for our domain value of 1,000, nowhere to be found. So this is undefined in our function h of t. So for our final example, we're going to be looking at how we use function notation using an equation in a problem situation. Let b of x equal -x squared plus 6x plus 6 represent the height b of a basketball x seconds after being thrown. So a couple things to notice. One, the height is being represented by b, and x represents the seconds after the ball is thrown. So our independent variable this time is x, which represents seconds, and our dependent variable is b of x, which represents the height. So now we're being asked to find b of 2, the height after 2 seconds. So to find b of 2, we are going to evaluate the function using the equation. We can use substitution to simply replace any instance of x in our equation with the value of 2. Now I'm going to be able to use parentheses to substitute, but I have to be careful to make sure I only replace the x with 2. So in this case, negative is going to stay out in front, and 2 is going to be in the parentheses because it's replacing the x. It's going to be squared plus 6 times the value of 2 plus 6. So now to finish evaluating, we are going to use the order of operations. You might remember PEMDAS. So since we don't have any operations within any of the parentheses that we drew, our first operation to deal with is the exponent. The negative is going to remain out in front, and we're going to evaluate 2 squared, which is 4. And we can also go ahead and move on to the next one, which is multiplication or division. Here I have 6 times 2, which is 12, plus 6. Since -1 really is what's out here, times 4 is -4, we can now go ahead and just add up all of our remaining values. -4 plus 12, or 12 minus 4, is 8, and 8 plus 6 is 14. So we get b of 2 is equal to 14, which means that after 2 seconds, the ball was 14 units above the ground. So now we're being asked to find the height after 5 seconds. Really what this is asking us, since we're being told that we are trying to find the height after 5 seconds, this means that x equals 5. Since we're trying to find the height, which is b, we're really being asked what is b of 5. I'm going to go ahead and evaluate using substitution, and after a bit of calculation, we end up with b of 5 equal to 11, which means that after 5 seconds, the ball was 11 units above the ground. Now, evaluating the domain and range in this situation can be a little bit trickier, so we're going to use the graph to take a look. So now looking at the graph of our function b of x, we can see that it actually has an infinite domain and an infinite range, but our situation does not have an infinite domain and range. It doesn't make sense to use negative values for x because x represents seconds after it was thrown. We don't have negative time, although it would be nice because I tend to miss my throws in basketball, and if I could go back in time a couple of seconds and just, not take the shot altogether, that'd be better. Anyway, since we can't go back in time, we only are going to use a positive value for x. Since our y values, or b of x values, represent height above the ground, we also don't need to use any of the negative values for y, because that would mean that our basketball somehow tunneled its way underground, and unless you're playing basketball with the world's heaviest bowling ball, this is probably not going to be a situation we need to assess. Our domain looks like it goes from 0, from x equals 0 to about x equals we'll go with 6.9. We'll round up a little bit. And our range looks like it goes from the bottom 0 all the way up to 15. So now, after analyzing the graph of our function while taking into account the situation, we can say that the domain of our function goes from 0 to 6.9 on our x-axis, including those two endpoints, and our range from 0 to 15, including those endpoints. So that's going to conclude our video lesson for today. I hope you guys learned a little bit of something about function notation. We're going to be using that throughout this video course. So please, once again, don't forget to like and subscribe to this channel so you can get content and help with your understanding of Algebra 2 throughout this year. And as always, I'll math you later.